Welcome to PhysicsNextbook. In this video, we shall discuss the Lagrangian and action of a relativistic free particle. But before we dive in, here are some bare basics for a proper perspective. The first thing is, of course, the generic idea of action functional and Lagrangian, what the least action principle says and how that leads to the Lagrange's equation. These have been already covered in earlier videos. Links are in the description. This Lagrange's equation represents the equation of motion of any mechanical system in a generic form. If we can provide the Lagrangian for a specific mechanical system, the Lagrange's equation will produce the corresponding equation of motion. So it is crucial that we learn to find the Lagrangian for a given mechanical system. Now, all mechanical systems can be classified into relativistic and non-relativistic ones. If the velocities involved, as measured by some inertial observers, is a significant fraction of c, the speed of light, let's say 1/3 c or half c, etc., they will treat it as a relativistic system. Otherwise, it is non-relativistic. For non-relativistic systems, the Lagrangian has a typical form, the difference of their kinetic and potential energies. The kinetic energy term for all the non-relativistic systems looks identical, half of the particle's mass times its velocity squared. But the form of the potential energy differs from one system to the next depending on the force involved. Such forces are called conservative forces. For example, gravitational force on a freely falling object or a projectile, or the sun's gravitational pull on its orbiting planets, restoring force on the mass attached to a spring, force of a static electric field on a slowly moving charged particle, and so on. There are so many examples. If no force is acting, we call it the non-relativistic free particle system, and its Lagrangian is just the kinetic energy term. In our previous video, we have discussed how the symmetries obeyed by such non-relativistic systems play a crucial role in fixing the mathematical form of their Lagrangian. The Lagrangian of a relativistic free particle is no exception. So let's start by listing the symmetries that a relativistic free particle admits, and see how they affect its Lagrangian, which for a mechanical system in general can be a function of space-time coordinates and velocity of the particle. The first symmetry is homogeneity of space, meaning to the particle every location feels the same. It can be in New York City or New Delhi or somewhere in the Andromeda galaxy, and its Lagrangian will be unaffected by its location. Basically, it will not depend on space coordinates. The second symmetry is the homogeneity of time. The free particle is free at all times, so no explicit time dependence in the Lagrangian. Then there is also the symmetry called the isotropy of space, meaning the free particle's motion can be in any whichever direction and its Lagrangian remains the same. Mathematically speaking, the Lagrangian can only depend on the magnitude of the particle's velocity, but not on its direction. And finally, since the particle is moving at a relativistic speed, it must obey the fundamental space-time symmetry of special relativity, that is, the Lorentz symmetry. Let's see what Lorentz symmetry really means. We have just discussed that the Lagrangian of a relativistic free particle depends on the magnitude of the velocity, and velocity is known to be relative. Its measured value differs in different inertial frames. So the value of the Lagrangian changes as we shift frames. Moreover, according to special relativity, the ticking rate of coordinate clocks in different inertial frames differ too. So time interval dt also changes as we shift frames. Therefore, as we Lorentz transform from one inertial frame to the next, we expect the LDT under the action integral to change. But it remains the same if the system has Lorentz symmetry. That's what Lorentz symmetry means. Notice why we had to consider LDT here, unlike what we did in the earlier cases of homogeneity and isotropy. There, the symmetry conditions were imposed on the Lagrangian alone, because these symmetries did not involve the change of inertial frame, so the dt did not change. Anyways, all these symmetries tell us to look for something which is Lorentz invariant, depends on the magnitude of the particle's velocity, and can be cast into this LDT form factor as a viable candidate for the free relativistic particle action. Now, if you are familiar with the earlier content of this channel, what should immediately come to your mind is the proper time interval d tau between two infinitesimally close events on the world line of a particle. The square of light speed times this proper time interval is equal to the space-time interval squared between these two events, and since any space-time interval is a Lorentz invariant quantity, so is this infinitesimal proper time interval. There are detailed videos available in the channel on proper time interval, its relation to space-time interval and their Lorentz invariance and so on. But very briefly, proper time is the time shown by the clock carried by the particle that we are observing. It differs from the coordinate time reading which is shown by the clock carried by us inertial observers. In a space-time diagram, coordinate time ticks at a certain rate along the time axis, whereas proper time ticks at a different rate along the world line of the particle under observation. The ratio of their ticking rate is known as the Lorentz factor that is completely determined by the relative velocity between the two clocks. So you see, the infinitesimal proper time interval d tau can be expressed in terms of the infinitesimal coordinate time interval dt and the inverse of the Lorentz factor because of the invariance of space-time interval, which is one of the fundamental consequences of the second postulate of special relativity. So is the infinitesimal proper time interval really a visible candidate? We can already see that it fits right into the LDT form factor, and we can easily read off the Lagrangian L as the inverse of the Lorentz factor with exactly the kind of velocity dependence that we want. However, 1 is a dimensionless number and so is the ratio V upon C, whereas any Lagrangian should have the dimension of energy. We have known that from the non-relativistic free particle Lagrangian, right? What is the dimension of energy? Well, considering the non-relativistic kinetic energy term, half mv squared, it's given by the dimension of mass times dimension of length upon time squared, coming from the velocity term. So our relativistic free particle Lagrangian must have another factor which is like mass times velocity squared. This new factor must be Lorentz invariant on its own, since the proper time interval d tau we started with is already Lorentz invariant. So our best guess is mc squared, since both c, the speed of light, and m, the rest mass energy of the particle, are Lorentz scalars. If this is indeed the correct Lagrangian for a relativistic free particle, it must reduce to the non-relativistic free particle Lagrangian half mv squared in the limiting case of v upon c approaching 0, that is small velocity compared to c. So we take the limit by expanding the square root term as a Taylor series of v upon c squared, and for small values of v upon c squared, retain only up to the first order in v by c squared. In the resulting expression, if we bring in a minus sign before the mc squared factor that we have just guessed, after a slight algebraic simplification, we do get the desired half mv squared limit. But in the limiting process, a new minus mc squared term has cropped up in the non-relativistic Lagrangian. Does this mean our scheme has failed? Let's assess the situation. If the minus mc squared times the square root of 1 minus v upon c squared really is the correct Lagrangian for the relativistic free particle, then the non-relativistic limit suggests that a non-relativistic free particle Lagrangian should have a minus mc squared term in it, which by the way we have never seen in non-relativistic mechanics. So can we somehow justify this extra piece of energy in the Lagrangian of a non-relativistic free particle? Clearly it is an additional constant term, so the derivatives in the Lagrange's equation wipes it out completely when the equation of motion is computed. Therefore, it cannot affect the equation of motion which dictates the particle's movement. So the non-relativistic low velocity motion of the particle has nothing really to do with the presence or absence of a constant minus mc squared term in the Lagrangian. No wonder that the theory of non-relativistic mechanics, which came from the observation of motion of low velocity objects, has no mention of this term. But surely we cannot claim the presence of a minus mc squared term merely for the convenience of our theory without some kind of observational evidence. And we must also understand what this minus mc squared term physically mean if it is really present in the Lagrangian. So if not the motion, is there anything else that this term can affect? The energy maybe? Fortunately, there is a formula to calculate energy from the Lagrangian. We have derived it in an earlier video, link is in the description as usual. Using that, we see if the extra minus mc squared term is indeed present in the non-relativistic Lagrangian, it adds to the energy of the particle. So, the total energy of a non-relativistic free particle is actually its kinetic energy plus the mc squared term. Consequently, this mc squared is the only energy that the particle has in its rest frame, where the particle is at rest by definition and therefore has no kinetic energy. Since the light speed c is a universal constant, the rest mass of the particle determines this energy. As in, bigger the rest mass of the particle, more is this energy value. So we call it the rest mass energy of the particle. This idea of the rest mass energy is in fact at the heart of the famous mass energy equivalence, which says mass is nothing but a form of energy and the two can be converted into each other. Einstein himself spoke of this mass energy equivalence in his 1905 paper, although he reached this conclusion not quite the way we have done in this video. Anyway, the experimental evidence for this came from the studies of nuclear reactions, which demonstrated that the mass of an atomic nucleus is less than the sum of masses of the free constituent neutrons and protons. This missing mass corresponds exactly to the energy release during the process of the formation of the atomic nucleus, as predicted by this mass energy conservation relation E equals mc squared. The nuclear fission and fusion reactions happening in labs all around the world, the infamous atom bomb, all of them are evidences of the existence of rest mass energy. So, we can safely say minus mc squared times the inverse of the Lorentz factor is the correct Lagrangian for a relativistic free particle. The corresponding action is its time integral, which is basically minus of the rest mass energy times the integral over the proper time of the relativistic particle, as we have discussed earlier in this video. To realize the beautiful physical meaning this action carries, remind yourself what the action principle says. An object follows that particular space-time trajectory which minimizes the value of its action. In the present case, minimizing our action means minimizing the total proper time interval. That is, the relativistic particle must take a path that makes its journey duration the shortest according to the clock it carries. Doesn't that sound the most natural thing to do? Hopefully you have found this video useful. Thanks for your time. Bye.